how we get these Green's functions, okay, and why it works out that we can take this little phi to be essentially a manipulation of the fundamental solution. Okay, so how does that work, right? So what I wrote makes it seem like, well, am I just setting phi equal to that? No, I'm setting phi equal to a shifted version and possibly reflected version of the fundamental solution. Okay, and that insight gives us what's called method of images. Okay, so maybe it's good just to start a new page for this part. So method of images. Okay, this is how we cook up our Green's functions for. We can do it a lot in general, but everything works out cleanly in a few kind of simple analytical cases. Okay. So what's the point? What's the point of method of images? The point of method of images is that the Green's function, okay, for let's say minus the Laplacian, right, can be directly calculated from phi of xy for some, okay, domains which are subsets of Rn. Okay, so let's start out with just showing the approach for the half Rn region. Okay. All right, so I'm gonna, kind of draw it like it's a box, right? Right. So the idea is here that we have U, okay, and we have some point x that lives in U, okay, and we're interested specifically in maybe what happens at the boundary in order to make sure that things cancel out at the boundary. So we'll call that boundary point x here, right? So our boundary is going to be du, okay? And in our case, that's going to be, x1, x2, xn minus 1, and then 0 here, okay? And the idea here is what is going to cancel out at this point? Well, it turns out because of the symmetry, right, of our fundamental solution, if we had a fundamental solution, okay, that we sort of centered here at this point x tilde, then because essentially our fundamental solutions usually just depend on the distance between x tilde and y, these two functions would have the same value here at the boundary point and they would cancel out. And that's the idea. You find the image point for all the points inside the interior of the domain. That's going to be given by a corresponding domain that lives outside of this region that has a corresponding point on the boundary that's going to, cancel out all of the possible non-zero values for your fundamental solution on the boundary. Okay. That's a hand-wavy way of doing it. We'll do it in more detail later. You can also do this with the unit ball, as we'll show. So let's say you have your domain is a ball. This is the origin here, okay? And let's say I have, some point here, I'll call it x, okay? And this here is a radius equal to 1, right? So here's u, here's our boundary du, and then let's say I'm picking a point y that lives on the boundary that I want to cancel out. I need to find some image point that lives out here, and maybe even some dilation of the argument of my fundamental solution so that that function will cancel out the value of this function here, okay? So obviously it's going to be more than just, flipping points over to the other side. In order to get the right arguments for phi, I'm going to have to, flip points outside of the ball and, maybe do some rescaling. Okay. So what the heck are we talking about here? So what we're talking about here is that we want to construct these image points. Okay. And we call them x tilde, and they're on the outside of U. Okay. For each x that lives inside of U. Okay. Phi of Cx, which could be some function of x, multiplied by x tilde minus y, is going to cancel the value of phi of x minus y. Okay. And that's going to be just on du. Okay. And Cx here is some scale factor. But essentially accounts for the fact that you may need to dilate your spaces in order for points to correspond to points, right? The unit ball as compared to outside of the unit ball, right? You can see that there's some warping of the spaces there that you're going to have to do, and that's what the scale factor accounts for, okay? But once you have all this together, g of xy equal to phi of x, I'll just write it as minus y here, phi of cx times x tilde minus y, okay? And the point is this thing here should be harmonic, okay, in y living in U, right? Remember, this thing is not completely harmonic because of the singularities, but this thing will be, right? Because as long as I put my singularities out here, right? If I take a value of y that lives in here, I'm never going to touch these image points that live out here, okay? So that's why we want to consider reflecting outside of the space, and then having a function that only has singularities out here in the outside of the domain that we're worried about. Okay. Let's see how this works in a concrete example. Okay. So let's just take the half space like I was talking about before. Okay. And then we'll see where we're at. Maybe I can also do the unit ball. So let U equal points in Rn, but such that xn greater than 0. Okay. So x is going to be, some x1, x2, xn. This is going to be in here. Okay. Now, what are these image points going to be? Well, we're going to call them x tilde, and they're going to look a lot like xn, or sorry, my x up here. But remember, right, xn should be a reflection, or sorry, x tilde should be a reflection, right, across the 0 axis here, right? So if I have a value of xn attached to my x value up here, then my x tilde value should have a corresponding negative xn value, right? So think of just, it like in 2D or something like that, right? If this was the point 2, 1, right, then my image point over here would be 2, minus 1, for instance. For example, in R2. Okay. So that's my image points, right? And fortunately, they do not live at all in the closure of U, right? So essentially, we're going to map all x that live in U to x tilde that don't live in even the closure of U, okay? Does this work, okay? Could I have picked some other values, okay? It turns out that for, sort of these flat boundary problems, you always want to sort of take the mirror image across, right? So if this was tilted or something like that, you want to have the reflection sort of be perpendicular to this boundary here, okay? Now, how are you going to choose this scaling factor that we talked about, Cx? Well, if I require that phi of x minus y minus phi of cx times x minus y, if I require that that equals 0, for x is in u and y is in du, okay, then I just need to sort of match my metrics of each of the arguments. What do I mean by that? Well, I want x minus y, which is equal to the sum from j equals 1 up to n, xj minus yj squared, square root of this whole thing, right? This should be equal to cx absolute value square root of the sum from j equals 1 up to n of xj tilde minus yj squared. Okay. So this is equal to Cx, the norm of Cx minus, okay. All right, so good. So let's say that we're right on the boundary, right? So the place that we're concerned about is right on the boundary. Well, in that case, the sum from j equals 1 up to n minus 1 has sort of one form, xj minus yj squared. And then I have the xn squared term. This is equal to cx now, the square root of the sum from j equals 1 up to n minus 1, xj minus yj squared, plus xn squared. Okay, because I'm just squaring it, so I get rid of the minus sign. So this implies that cx can actually be equal to plus or minus 1. And so phi of x minus y, right? I can just choose it to be 1, so I get phi of x tilde minus y on x is in u, but y is on my boundary, okay, du there, okay? So g of x, y is equal to phi of x minus y minus phi of x tilde minus y, okay? And this should look familiar, right? So if you recall our heat equation with Dirichlet boundary conditions on the half line, okay? This is very similar to what we do in that case, right? We just subtract off the reflection of the solution across our boundary point, okay? So just to show that this works, right, minus the Laplacian with y, it should work for x as well, is equal to the delta distribution, well, delta in the sense of distributions, right? Where x and y are in U there, and then g of xy, as we've set it up, should vanish at the boundary, right? Where x is in U and y is on the boundary there, okay? And this is true essentially since x tilde is not on the closure of U, right? Phi of x tilde minus y is harmonic in y and U, okay? And so, yeah, so we don't get any delta contribution from the little phi term, right? But we do, which is essentially this term here, right? This is our little phi y x term here, which should also be equal to little phi xy, okay? So I think we're at time. So let me just talk back through how that worked, right? So we said we know the fundamental solution to our PDE. We know that that's going to be part of the Green's function. The correction, in order to account for the boundaries, needs to be a function that is going to have the same value, okay, for the same value of x and y when y lives on the boundary, only when y lives on the boundary. The way we do that is we build a function outside of here whose tail sort of hits the boundary here in the same way that the fundamental solution does from the inside. You get cancellations always along the boundary in that case, and the singularity that you would get here from y equaling x is not a problem because x tilde is always outside of the closure of U, okay? So that works, and that is then your Green's function, right? So this is your Green's function in the case of the half space, okay? On Monday, we'll talk about working this out in the case of the unit ball. And then on your homework, it'll probably be homework 7, you'll practice building these Green's functions in the case of the intersection of domains like this. So if you have a half ball or something like that. Okay, so that's it. See you on Friday.